Thank you. No, I appreciate the opportunity to come out and speak. I was at the airport this morning. The plane coming from Houston was full. I called my wife. I was like, a lot of people for Tuesday morning, and she's like, oh, they're probably all going to see you speak. So clearly looking around, probably not. I don't recognize anybody from the flight. But what we're going to talk about, survey management. So what is survey management? What are survey corrections? Why are they important? Why should we be using them? So managing survey-related activities performed during drilling processes is extremely important to an oil and gas life cycle. We talk about it as a survey life cycle. It helps in wellbore trajectory planning, directional survey planning, relief well contingency planning, standard survey operations, data management, which is extremely important, especially when you look at going into existing fields, trying to pull out as many hydrocarbons as you can from those existing fields, infills, things like that. We're going to talk a little bit about corrections and tool error models, kind of what helps feed where you're planning your wells, your anti-collision, things like that. And then survey quality control, which is kind of the big thing that we do at Superior QC. It's in our name. We like to kind of pride ourselves on our quality control. When we talk about survey correction algorithms, we talk about them in a generational approach. So right now, we see there being 4 main generations of survey correction algorithms. And we'll go into depth on each of these. So the first being, your first gen is field acceptance criteria. So this is about 40 years ago, grand idea of, hey, we should be qualifying these surveys that we're using. So how do we go about doing that? We're going to look at, what our expected gravitational field, magnetic field, and our formation dip is. And we're going to say if that's a good survey, yes or no. There's no gross error detection. All you're doing is looking at the actual data that you're receiving. Some of the problems with that. So this is going to be an example of field acceptance criteria working. So if you look here on your x-axis, you have the dip. On your z-axis, it's the your B total, so your magnetic field. That box represents a field acceptance criteria zone. So if your survey is falling somewhere within that zone, you say it's a good survey. In this case, this black diamond out here to the right, that shows that it fell outside of it. There was error within that survey, about 0.72 degrees of azimuth error. That survey failed. So this was a good example of field acceptance criteria working. The problem is that when you look at those different contributing factors, there's about 27 different things that can impact your survey placement. So when you talk about just looking at 3, there's 24 others out there that could possibly have some significant error in them. Same type scenario, a different azimuth. This was about 800 nanoteslas of drill string interference, which is it exceeds your ISC WSA error model. So if you're not familiar with ISC WSA, it's Industry Steering Committee for Wellbore Survey Accuracy. What they do is they establish the IPM files that actually drive your anti-collision scans that are used in planning, things of that nature. So this is a survey that actually falls within that box. However, there's some other error terms in there that are impacting the placement. There was actually almost 2 degrees of error in this survey set that we looked at. So again, it's not a gross error detection. It's basically a simple way of saying, hey, I'm looking quickly at the data. Is it good? Yes or no? And then moving on from there.
So, can you take a question?
Yeah, for sure.
So on that box, when you're defining that would have to be local to where you're.
Yeah, the problem with field acceptance criteria that I see is that there's not a standard out there. If you ask a directional company what they're using for field acceptance criteria, you're going to get a wide variety of answers.
Yeah, I was saying, is it dependent not only on local areas, so the field magnetic strength and obviously
sure,
all that, but also the tools and tool placement, like you were saying, you're seeing some interference.
Yeah. So your IPM tool codes, those codes that you're actually using to help plan these wells, that your well planners are using, that everybody's using to say the well is going to be here, those are defined. Those have defined limits, a 3 sigma limit that says if you exceed this, you could exceed that ellipse of uncertainty that you're assigning to that specific wellbore. So in my opinion, you should never exceed 2 sigma on the IPM. The problem that I see with directional companies is that there's either people don't know what field acceptance criteria is that they're using, or they're using defaults that are set into the surface box. And if they're not changing those, bench tree, for example, you got 5,000 nanoteslas is the default qualifier. So everything's going to be a green flag. you're never going to see a bad survey. So paying special attention to that is important. Again, another reason why you should have a third-party quality control on the surveys themselves. Definitely open forum. If you have questions, please raise your hand. I'm more than happy to stop and dive in a little bit. Second generation, so we talk about single station correction. What is done here is that you're throwing out your magnetometer Z axis, so you're assuming that value is going to be bad. All you're solving for here is your axial magnetic interference, your drill string interference. The problem with this is that you're looking at each survey in isolation. You can have some BZ estimates that vary pretty wildly over the course of a single BHA. So it's very difficult to nail down exactly what the error source is, other than you've got some type of drill string interference, right? This is about a 30-year-old piece. The folks that had written it got together and said, hey, you know what? If we're looking at axial magnetic interference, that should stay the same. Your BHA isn't changing while you're downhole. You may have some metal properties that change within that BHA, but you shouldn't see a significant shift in the in that AMI source. So it should be pretty much the same. So if we can estimate that value, we can estimate a handful of other error terms at the same time. So this is where we get into third generation, which we call multi-station analysis. It's widely used in the industry today. The algorithm itself is about a little over 20 years old. What you're able to do is you're able to take a handful of error terms and solve for those all at once. Looking at it, there's different pieces to it. It works off of what's called a least squares technique. So what you're doing is you're solving a linear equation by inverting a matrix. I know that probably sounds like just a bunch of words that I'm throwing out there, but the problem that comes into play there is you come into a conditional formatting issue. So the number of error terms that a computer can solve for simultaneously is limited by the algorithm itself. When you look at it, this is kind of an example. Let me dig in here a little bit. So can you see give me just a second. All right. There we go. All right. So looking here, your upper limit for computers is right about here, 10 to the 16th power. Anything other than that, your solution becomes numerically degraded. So it basically becomes a solution that can't be trusted. You're still going to get a result. However, the legitimacy or the accuracy of that result comes into question. When looking at multi-station analysis, about 6 error terms is what the upper limit is. When you talk about how many error terms there are, again, I said previously, there's 27 different terms. So if you choose 6 of those, you're saying that those other 21 error sources have no error at all, right? So again, if you have significant error that's in one of those, that could impact your placement. That's going to possibly place you outside of your ellipse of uncertainty, possibly move your wellbore hundreds of feet in either direction. So the problem with multi-station analysis, another problem that we see is that it's human interpretation. So you have an analyst that's sitting there and they're choosing subsets of the data to solve for. So they have a data set come in, they choose, between, 3 to 6 error terms to solve for, and then it's run through a program that's going to give you a result. Again, human interpretation is a big piece of multi-station analysis that we wanted to move past. But there's thousands of possible error combinations when you start talking about 27 error terms. There's 5,039 different solutions that you could choose. So as a human sitting behind a computer screen, trying to pick those, trying to do it in an expedient manner to get the survey back to the MWD in the field, it could become a problem. This is what kind of a normal multi-station analysis software looks like. Chad Hannock, who's my president, he came from NASA. He wrote the guidance navigation control systems for the Orion spacecraft. It's the same trajectory optimization algorithm that the Artemis missions are going to use to go to the moon. He started as an MSA company. Superior QC was an MSA company when it was first brought into business. He saw the issues that kind of lived within that the human interpretation, the limitation of the error terms that you're solving for, all those were things that were impactful to him that he saw as we can fix this, we can improve it, we can get better. So let me skip ahead a little bit here. I apologize. So again, we talk about the human piece. You have all of a multi-station analysis solution has some level of validity to it. What you're trying to do is you're trying to find the most accurate placement, right? We want to understand where the well is to the best of our ability. So with FITR, what we call FITR, it's fault detection, isolation, and recovery. We took out the human piece of it. So this is a cloud-based machine learning algorithm. We solved the problem of the conditional numerical conditioning. So we're not limited on the number of error terms that we're solving for. So we're solving for all 27 error terms simultaneously. It's all done in just a few seconds in the cloud and then delivered back through either web front end or API to the user. The piece that we saw, the benefit that we saw with this is that you're not relying on the knowledge of that person that's sitting there choosing those subsets to solve for. You're not relying on a human having to turn around, multiple, if they're looking at multiple different wells, a time delay to the field or anything like that. What we do is we're looking at these 27 error terms. So this is what we solve for every time. So left to right here is magnetic reference. So your magnetic reference field is going to give you your delta B, your Excel biases. So you have accelerometer biases on your X, Y, and Z scale factor, accelerometer scale factor X, Y, and Z, delta B reference, delta dip reference, again, magnetic reference errors. You have your declination error. The only way you can solve for a declination error is with a gyro. You do need an independent third-party tool to do that. And then the same thing on the magnetometer side, your magnetometer bias and scale factors, as well as bend, twist, and non-orthogonality. So when you talk about bend and twist, that's how the MWD sensor is in the collar. When you talk about non-orthogonality, you talk about how the sensors are. So that brings in calibration. So that's another thing that Stan and I actually were talking about before, is that a lot of tools are calibrated at room temp. What happens when you get down hole is obviously heat is going to be applied to that tool. That's going to affect the calibration. So how is that tool, working down hole? If you're ignoring that, if you're just assuming that your calibration is correct, you could possibly put yourself into a bad situation there.
So what are you doing then? You're calibrating it under different conditions in the lab or in the shop, or you calibrate it on the field?
So you're looking at what you expected the reference to show you, what the tool is expected to show you in real time, and then taking those measurements from downhole and comparing those. And that's how you're able to see if there's bend or twist or non-orthogonality. You can measure that based off of the bias that you see within your real-time measurements.
Then how do you account for the heat, the difference in temperature?
So that's doing is that's affecting your calibration. So that's what we're using the algorithm to help see that change in what should be expected from the tool and then what's actually being shown.
And then how do you may get into this, but how do you calibrate, or how do you measure the current magnetic field on that day and that time that you're actually taking that measurement?
Yeah, no, that's a great question, right? So the magnetic field's shifting all the time, right? That's why your magnetic references are always changing. Usually everybody's using pretty much an HD, a high definition geomagnetic model at this point. Those are updated usually about every year. So the Earth's magnetic field shifts about a scale within your IPM file that needs to be updated. It's over about the course of a year. What we do in the U.S., you don't see as much of a change. It's not as fast. When we talk about some of the rigs that we operate on in Alaska, North Sea, things like that, we use what's called IFR2 or double IFR. What you're doing is you're taking measurements from an actual station that's measuring the Earth's magnetic field every minute, and that's what we're using as our magnetic reference field. Is that answer?
Yes.
Perfect.
Thank you.
Yes, sir. I'm going to skip the correlation coefficient matrix because it makes my eyes go cross-eyed. But what this is what our results look like. So what you're doing here is you're looking at all of those different possible combinations that you could possibly get from your surveys, and then those are weighted. So again, not having a human just pick one solution and saying this is what the answer is. looking at all those thousands of possible different solutions at once and saying this is the most statistically accurate placement of your wellbore, and that's how we deliver our result. Does that make sense? I hope I'm not talking in circles on this. One of the problems that we still had to address was TBD, right? So how do we fix the up, down, or vertical uncertainty? So has everyone heard the term the Stockhausen effect or Stockhausen corrections? Ed Stockhausen, has anybody read his papers? So Ed's been around for about 20 years. He retired after he gave the industry this huge problem to solve. And basically what it is it's talking about how we use minimum curvature traverse to calculate your wellbore trajectory. So what you're doing is you're taking two surveys, you're connecting them by a smooth arc. So assuming there's a smooth arc between those surveys, everybody in here in the room that's ever been anywhere with drilling knows that there's no smooth line between two surveys, right? You're going to slide, you're going to rotate, you're going to have rotary build and drop tendencies, you're going to have motor buildup that's going to move you up and down. So how do you model that? Looking at this, one of the issues that came up, if you slide to start your survey or start your stand and then you rotate out, you're going to come in higher than what you think you are through minimum curvature. The exact opposite, if you rotate to start the stand and then you slide it out, you're going to come in lower. And that's just based off basic physics of how the BHA is operating. So what we came up with was how can we model this? How can we show that structure that's occurring in between your static MWD surveys? So we came up with a solution. It's called Hi-Fi navigation. And what we do with it is it's our 5th generation solution. What we're able to do is not only reduce your horizontal uncertainty, but also your vertical uncertainty as well. So what you'll have is you'll have a survey, slide, you'll rotate down, you'll take a survey. From that survey, we're going to pull in all the information from the EDR, and we're going to use that to help calculate a real-time motor buildup rate, your rotary tendencies, so your build and drop, and then your rotary walk tendencies. And then we're going to project forward from there. So real-time projection a bit with trajectory points. So now instead of having a survey at 95-foot course lengths, we've got a survey every 15 feet. So we're modeling that structure that's occurring in between your static MWD surveys.
Do you have a true survey every 15 feet, or is that
A calculated trajectory every 15 feet. Yep. What we'll do, we'll project that out, drill down the next stand, we'll take another survey. Based off of where that new survey is, how that changes our tendency estimates, we'll refine the wellbore behind us, right? And then help, again, push that projection further out. What we've seen in this was a case study that we did kind of early on in the process. The blue line that you're seeing down here, these were the surveys that were reported to the Railroad Commission. This green line here is what we modeled with Hi-Fi nav. We went in, we looked, what we saw was there was a significant rotary build tendency that they were fighting throughout the entire lateral section. They would slide, build way up, and rotate, knock it down. Slide, rotate, build up, knock it back down, over and over and over again. So what was happening is that they were getting all of this structure in between those surveys that was above the inclination survey line. When they would slide back down, it would go away. So they weren't capturing it. So we saw about 75 feet, 1.5 degree build tendency. We ran a gyro on it and it matched up perfectly. Geos thought that they were just getting ratty gamma. So the interpretation is improved significantly by this. It's a great way for geology to kind of see what's happening in real time. This is mostly done on conventional motors. We have done it with rotary steerable as well in South America. So nothing that we've done. We haven't done too much in North America with rotary steerable, but South America we saw about half this, about 30 feet of TVD delta between those surveys. So this helps with drilling, this helps with geology, and it also helps with completions and production. So if you're able to take a much more dense survey log, it's taking, instead of 200 surveys, you're handing 1,500 surveys to your completions teams. They can see those tortuous sections. They can see if they're having issues getting casing to bottom. It's going to help them identify that. It helps with ESP, rod lift placement. So you're not going to burn out pumps and things like that if you're putting them in, kind of a bad situation. And then the next piece we're starting to work on, and this is kind of the future of what we're going to, is it's called guidance, hi-fi guidance. Again, Chad Hannock, he came from NASA. In space, you have sensors, right? So same thing downhole with MWD, you have these sensors. You know, where are we going? So you're using accelerometers and gyros in space. Your navigation piece is where am I going? You know, where am I trying to get? I have a target that I want to get to. Same type thing with same with drilling. What guidance am I using to get there? So how are we getting to that target? How are we using our fuel? So in space, you can only take up a finite amount of fuel, right? You're limited on based off of weight and cost. It's very expensive to take fuel with you. So you have to minimize your delta V or your delta burn to get where you're going. Same thing when you talk about drilling and you correlate all this to drilling, is that you want to be able to rotate as much as you can, right? When you're sliding, you're taking up more time. Rotation, you're going to gain a lot more ground. So what we looked at was optimizing slide rotate algorithm. Like I spoke about earlier with the trajectory optimization algorithm that Artemis is using, we took that same math and applied that to downhole drilling. So we're using the same optimization math to help project forward where you need to slide, where you need to rotate in a wellbore. So what we've seen increased ROP by sliding less. This was an example that we saw. Guidance was showing the DD that, hey, look, you need to slide 2 times here in the lateral. So they came in, they had a little bit of a drop tendency, slide here to counter that, bump it back up again here, and then at the end of the section, they had a drop. What wound up happening is the night DD came on, he saw, hey, I'm dropping, I'm gonna go ahead and rotate out of this. So they started sliding up. They wound up getting up too high, had to slide back down, and then another 3 slides to finish that section. Yeah, night DD. It's always the night DD.
Blame it on the night DD.
Absolutely. No, so again, this is just, you know, it's a forward-looking algorithm. We do have short and long-term filtering that we run over this. We plan all the way out to TD. So that driller is able to see his slides all the way out to TD. As we get more information, as that hi-fi nav is updating those tendencies that it's seeing, it's updating those slides, but everything is utilizing a window that's based off the directive from the drilling engineers.
Can I ask a quick question?
Sure.
How is it determining like when you need to slide, when you need to rotate, and is it continually updating based on the survey data you're getting, or based on how effective the slides are? Kind of how is it?
Yeah, no, it's a great question. It's all of that, right? So we update the tendency estimations through the surveys, right? Because that's what we're modeling, right? Where do we wind up? We're pulling all that information in real time through the EDR. So we're tied into the rig. We're getting all the torque, weight on bit, when rig states and everything like that. So that's feeding into the algorithm. We're pulling in continuous azimuth. That's also feeding in. So that's what's telling them you need to start here, stop here, and then it also will grade that slide as well in real time. So it's telling you how well you're holding tool face. If the slide was efficient, then you know that'll feed into how well can the DD hold the slide. It'll take that into account the next time. Maybe we need to add a couple extra feet because you're not holding slides as well. You're not as efficient in your slides. Yes.
How does the data relate when it's rotary steerable versus conventional? I know the tools are the same. I just want to know how
for sure. So the nomenclature we use obviously with conventional slide rotate. When you're talking rotary steerable, you're talking steer non-steer. So you're still putting in like an azimuth hold, but how well is the tool holding that azimuth, right? Are you getting pushed around? Are there tendencies that are pushing that rotary steerable around? If there's an ink hold or azimuth hold, that's what we'll grade off of. But what we see is that when the tools are given a command, as opposed to when it's downlinked and accepted and then actually performed, that's where we'll go and we'll model it. We have a physics-based model that we run the command sheet through, and that creates a pseudo slide sheet, basically. So we're changing that steer non-steer into a slide rotate kind of vernacular and feeding that into the algorithm. Yeah.
I got a quick question.
Sure.
I believe it's on the previous technology, but it says there's no longer a no-go zone. You go into a little bit of how y'all. Yeah.
So when you talk about multi-station analysis, it has a hard time drilling east-west. So so that's your 30 degrees plus or minus of east-west, which is we call it an exclusion zone or no-go zone. What problem that you're running into is you're trying to determine what the Earth's magnetic field is when you're running parallel.
How do you eliminate?
Right, how do you eliminate it? Right, so by us looking at all of the different terms simultaneously, that allows us to get through that. So we're looking at that. Not only are we looking at the run that we're on, we're looking at the other runs as well. So if you have a magnetic reference that you should be seeing, that magnetic reference shouldn't change over the course of a well, right? 5 to, maybe 10, 12 days. Up here, Oklahoma, a little bit longer, right? You're a little bit longer to drill, but your magnetic reference should stay constant throughout those runs. So if you're seeing a difference there, that helps us kind of solve that problem as well. Just a combined approach to it instead of looking at just one subset of data. Another piece we've seen out of this with the guidance is increased ROP with increased footage in the window. Apologies. So we've got probably about a little over 100 wells that we've drilled with guidance in a shadow mode as well as in an actual application. What we've seen is significant a reduction in slide percentage, about 30 to 50% slide percentage reduction. The amount of the well in the window has increased significantly from about 70 to 80% to 95% is our average footage in the window. So again, it's utilizing everything that the well is giving us as far as information. I think for a long time, a lot of data has been pushed up and nobody's really known what to do with it, right? You go and you look and there's boxes and boxes of stored old well information that was never used that you can take in now through the use of computers and different programs to analyze all that rapidly and utilize it and push it back to the field as knowledgeable information. This is just another example of some of the information we saw staying in zone. So this was a well we were 100% in zone. The adherence to guidance on this was about 70%. So the DD was still saying it sometimes, hey, I want to slide a little bit less, maybe a little bit longer. Not necessarily targeting a specific tool face that we were saying, but on this we were 100% in the window, and that's what we see normally is very good adherence is going to lead to a reduction in slide percentage as well as increasing footage in the zone. And at the end of the day, this is all automation integration, right? So this is feeding one big brain. So we're tied in. Again, this is all cloud-based. No personnel, no equipment on location, just tying into the information that we have that's available to us and utilizing it in a meaningful way. Through Fitter, Hi-Fi Nav guidance, and then Hi-Fi control will eventually be Patterson's automated rig control piece. I think that's the goal is to move to rig automation, eliminate, I don't want to say eliminating people on location because everybody gets scared when you hear that, but making it a more efficient process. So, and that's all I had. Questions?
Yeah, so you touched on how minimum curvature is inadequate in dealing with that, right?
Sure.
So you're making the projections, you're not making them minimum curvature, you get around.
You are still using minimum curvature. It's just over a much shorter distance, right? So there's less of an opportunity for a structure to be missed within that. So projecting it over 15 feet as opposed to over, say, like a 95 foot or 190 if you miss a survey.
Okay, then my second question is about qualification of the surveys themselves. So how do you negotiate that between what you have to report from and what is going to be accepted by the government versus what the director company who owns the tool and are making all the measurements can sign off on in your corrections?
Yep, absolutely. No, great question. So what we're doing is we're helping with that EOU reduction, so that placement, improving that placement accuracy. What we're doing is we're using a 3 sigma approach to the final solution. So wherever we say that well is, when we back out the error, we're still running a comprehensive look at the data to say, yes, we fit within the ellipse of uncertainty that we're assigning. It's going to be a significant reduction over what your IPM is able to give you, just because if we were to do like an error model for every single well, it would take forever, right? So we still have to abide by the EOUs that the IPM models are crafted, that are approved by the ICWSA, which is our Gen 5 models. We have to abide by that, but what we're saying is that where our solution is, we can confidently say that we're fitting within where you think you actually are. Does that make sense?
So are you saying that your final solution falls within the vendor or your client IPM, like Superior doesn't provide an IPM?
We have our own IPM files. Yeah, it's what you standard, your OWSG MWD plus your magnetic reference plus, if you're running SAG, and then we have what's called plus fitter. The reason we had a different from plus fitter and plus MS, which is what your multi-station IPM is, we thought that the Rev4 models were a little bit too optimistic. So we actually created a model that was smaller. So you're using a smaller model to plan off of, just because we didn't think that you could really fit within what the plus MS was showing at the time with the Rev4. Now with the Rev5 changes that we made with Air Model Subcommittee, they're going to be larger now. They're going to be a lot larger. So you're going to have to actually plan in more spacing for Rev5 over what Rev4 was giving you.
Okay, so the client, Superior would be able to provide like IPM.
Mm-hmm.
This is what.
Yep. Yeah, we have our own IPMs, but it's still it runs to what the ISC WSA guidelines are. Yep.
So you mentioned that the directional drillers are taking those recommendations that you have on how to slide, how long, things like that, based on their capabilities or accuracy. How are you overcoming, or are you seeing any pushback to those?
Yeah, absolutely.
Feedback, and how do you see overcoming that based on their experiences, things like that? Yeah,
I think the number one thing that drives the oil field is ego. So having to having to overcome that, right? that was huge, right? Adherence, acceptance, trusting in the solution that it's giving you, and not seeing it as competition for the DD. It's not something that we're out there to replace DDs. That's not the intention of it. What we're doing is we're taking away those calculations that they have to do, looking at a lot more data than they have the capabilities of doing at one time, and letting them focus on different tasks on the rig. So yeah, adherence is our biggest thing. When we start with a customer, we'll get 40% adherence, maybe if we're lucky. That's like really, really good. But the more they use it, the more they trust it. They see that, hey, this is something that could be beneficial for me. It's helping me out. We start to see, some improvements there.
Quick follow-up.
Mm-hmm.
Do you have any kind of way for them to provide feedback, such as, a very difficult drilling area, we know that this formation doesn't lie well, things like that. Do you have an ability for them to bring that feedback and input that?
We do, yeah. So we have a 24-hour center that all this is being run through. All of our products are supported through this center, but we have one that's dedicated specifically to guidance. The folks that we put in there, we have 30-year guys, 30-year DDs that have drilled all over the world, that are familiar with different zones, that know, hey, we're possibly going to see some issues here with what's being recommended. So let's get in front of that. We'll communicate. It's definitely an open channel back and forth between them and us. Again, it's not the law that, hey, you have to do this. This is what, looking at the current data that we have, this is the best recommendation that we can give you to drill that well in the best way possible.
So, say you're correcting the latest NWE company surveys, north-south well, your EOU size compared to a spinning mass gyro.
Yeah. EOU size, probably not. Yeah, we don't get much. You're not going to get much reduction north-south, right? You're going to get more accuracy. We're able to reduce the vertical ellipse, but horizontal ellipse usually don't see much. Maybe more than probably 30 to 40% reduction over a standard plus MS EOU. The way we can compete with the gyro EOUs is when you start talking about additional surveys, right? Either through dual telemetry or through hi-fi nav. We are able to reduce up to about 70% EOU through that. That's vertical and horizontal.
You say you can be 70% smaller than
70%. No, 70% smaller than your standard ellipse.
Okay.
Yeah. We did. let me get a card from you. I'll send you a case study that we did. Yeah, we actually had a larger reduction than the gyro. So yeah, I'll get that over to you.
Perfect.
Cool. Anybody else? All right, I appreciate it. Thank you.